Welcome to week 7 live session of molecular spectroscopy of physical chemist perspective. So today our agenda would be to solve a few questions, which is both numerical and as well as in terms of general questions, derivation kind of questions. So these questions are actually the I have given these questions to you in the previous discussion sessions on the Saturday actually. So these questions are set up by Professor Datta for a mid-semester class. Along with these questions, I have also collected some questions from this year's molecular spectroscopy part. These are almost a similar kind of questions, easy questions. So we'll try to solve these questions and try to get a revision what we have done so far. And then from the next week onwards, we will again go ahead with the symmetry and other problems. So let us start with the easy problem in our hand. So first, it is given that calculate the bond length of a diatomic molecule AB. So, and what are the things given? The masses are given 5 mu and 40 mu. And what is given? Spacing between two successive lines of a microwave spectrum is given 8 centimeter inverse. So we know that rotational constant. So actually I'm starting with the easy problem so that we also get some momentum. So you know what is B? It's H pi square mu r square C, right? So here what are the things given? We can calculate mu. Mu is m1 m2 by m1 plus m2, which would be 5 into 40 divided by
200 by
5.
45.
Yes, in AMU. And then it would be 200. Oh, sorry. Forty-five into 1.66 into 10 to the power minus 27 kilograms. And what are the things given? That B is given. No, not B is given. 2B is given. That the spacing between the any two successive lines. And what is given? Rigid rotor. So there is it is 2B is equal to 8 centimeter inwards. So B is 4 centimeter inwards. So your R is going to be under the root H 8 pi square mu B and C. What is H? Planck
Six.
constant.
Yes, Planck constant.
It's
6.63
convert.
into 10 to the minus 34 joule second.
Right. 8 into 3.14 square. Mu we already know 200 divided by 45 into 1.66 into 10 to the power minus 27 kilograms into B is 4 centimeter inverse and C is 3 into 10 to the power 10
Centimeter per second.
centimeter per second. And joule is Newton meter, then Newton meter because it is work done. Work done
Yes.
is force into displacement. Then Newton is kg meter square second to the power minus 2. So it would be, instead of joule second, I can write kg meter square second to the power minus 1. So kg and kg gone, second inverse gone, centimeter inverse, centimeter gone. What are the meter square will be remain in the numerator and it will come out of the square root as meter. So we'll just see what is the value is going to come, but 6.626. Let us at least keep it in terms of the order 10 to the power minus 34 minus 27, it will be minus 7, and again 10 to the power 10 is there, so it will become 10 to the power 17. 10 to the 10 to the minus 7, 10 to the minus 17. Minus 17, even 100 is there, minus 19. And then we can enter outside.
The answer I got was 0.973 angstrom.
Okay, so let me write it directly. Point
973 angstrom.
angstrom. Uh, this is in nanometer, how much it would be? So
9
1
point
angstrom is 10 to the power minus 8 meter, right? Or centimeter.
minus 10 meter.
Yeah, no. 1
Angstrom is
nanometer
10 to the
is 10 to the power minus 1
minus
angstrom,
9.
right?
Yes, yes, yes.
Right. So this is how much? Or in
9
case of
point 9.73.
so or in terms of picometer, it would have been 97, right?
Yes,
97.3,
yes.
right? Something like this. So I think when we were solving the problems, we were doing it in terms of picometers, I guess, what I remember. Anyway, whatever unit you comes up with, even with the meter also, it is fine. So yeah, that's the correct approach. So this is done. Now the second part. How will the spectrum of the molecule in 1A change if the temperature is lowered to 0 K? So what is the maximum population would be, or what would be the maximum population, P or maybe PJ max? Population at max is, we know the formula, right? What is that? KBT
KVT by
2
H.
BC, right?
Yes. Minus half.
Minus half. So if the temperature is 0 Kelvin, then you can see it is coming as population. So J max, not PJ max, sorry. J max is, J max is showing to be, actually it is coming as to be minus half, but you know, as we discussed earlier also, that it is not J max or J are not continuous.
Yes.
So we have to go to the nearest
Integer value.
integer value, and that is 0 in this case, and it cannot be negative. So J max can be 0. 0 means it is in the ground state. So all the
Yes.
population is at J equals to 0 now, at 0 Kelvin. So if my selection rule tells me that delta J can be plus minus 1, so now what is the possibility? So only transition from J equals to 0 to J equals to 1 is possible only. And so as there are 2 marks are there, so not only you have to show one line with obviously with respect to wave number or something, intensity versus intensity. So where the point will come. So in this
2B.
transition, what is the delta E?
2B at
2B, right? And 2B is
yes.
given to us that 8 centimeter inverse.
8 centimeter inverse.
So you have to mention that also. We are expecting only one spectra, one transition, one spectrum, distinct spectrum, and That too at 8 centimeter inverse. So that's a correct answer. Okay, I hope if this is correct, then we can go to the next question. So the next question deals with uh, so the next question says the energy of a non-rigid rotor in centimeter inverse is given. Now, as non-rigidity has been involved, you see now the energy is Ej is B J J plus 1. So in case of uh, let me write it down once. That so this is for a non-rigid rotor. Sorry, yeah, for a non-rigid rotor. So first question is what is the starting point of the derivation for the correction to the energy of a rotor due to non-rigidity? Please note, we don't have to do the derivation, but what is the starting point? Starting point means, see,
We have
when
to
we are
consider the centrifugal part,
centrifugal, right?
distortion
So,
part.
yes, so you need to so if I have to write it in maybe one or two words, so it would have been that if for a non-rigid rotor, there is a change in the bond length from the equilibrium bond length. That is maybe our equilibrium I could. So that is what we also discuss in terms of when we discuss vibrational spectroscopy, right? So there we discuss the oscillation. What is the how much what is the change in the bond length? So that is what we also discuss in case of vibrational spectroscopy also, and there you can get a relationship. I mean, the relationship in terms of the force constant and uh, this, I think D is there you can establish one relationship between them. So now the correction, suppose the correction to the energy of the rotor, non-rigid rotor, arise due to centrifugal centrifugal
Distortion part.
force acting on the centrifugal force. So in this case, from a two body problem, we have converted it to a one body problem, right? So actually, in case of this, you can think of that your mass is this is your mass, this is your equilibrium distance, and it is moving. As it is no longer a non-rigid rotor, so some centrifugal motion is centrifugal force is acting over the mass. So that is what actually leads to this. This D is what centrifugal constant or the
Yes.
centrifugal distortion constant, right? So
No, sir. Centrifugal force is always there. When you rotate something, centripetal and centripetal force are
they are in equilibrium.
yes, yes. But when it will dominate means there is some kind of deviation from this equilibrium. In that
Yes,
case, this centrifugal distortion part we have to consider this thing.
yes. So this is your force constant, and this is how much difference is there. that would be equals to something like, so there is a, so I will try to cover this derivation maybe. So this derivation is actually, I think, taught not in the class, not in the class definitely, but in one of the recent course. I was a TA of that course. I will try to see my notes if I have it. I will try to discuss this part once. Then it will be maybe beneficial. I think you already know it, but maybe others who are watching it on YouTube, maybe it will be beneficial for them also. I also forgot the exact derivation. I will look at it. One.
Sir, I have a question. This kind of do I expect this kind of question in
No,
this NPTEL?
no, no, no,
NPTEL.
no, 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 no,
Okay.
not really, not really. Maybe some conceptual question can be asked, but you don't have to write. You do not have to write anything. This is just
Do, yes, yes. Do you have the earlier year question, previous year question for this
the,
NPTEL exam?
sometimes the question actually get repeated. So
Okay, okay,
I
okay,
don't have it with me. But even if I
okay,
had it, I would not. I do
okay.
not have the permission
Yes, yes.
to
No
share
problem,
it.
no problem. Okay, no
Yes.
problem.
But let me tell you, it is very easy.
Okay,
If you are solving the daily assignments, then
yes,
and obviously there are some mistakes right now in the assignment problem, but when the exam will come, all those will be mistakes will be taken care of. So don't worry. If you are doing the assignment properly, then you will find them very, very easy. So this is
yes.
just for
But
clearing your.
I am just found myself these difficulties. The symmetry part. I can
Oh,
I have bit of knowledge of symmetry and all these things, but this do you have to really know? Really, I have to know this. Yeah, what kind of symmetry species are there and their point group and table. We have to know, or
so whatever has been taught in the lecture notes, na, mostly that will come. Means no other molecules. Means what I from my experience.
yes,
I think I don't remember the exact molecules what has been taught yet, but it's not hard. What have been taught, those kind of molecules will only come. Means you don't expect completely different molecules. You are thinking about the point group. That situation won't arise.
okay, okay,
No, in that situation won't arise. And for symmetry and point group, there is a separate course by Professor Datta is also there in NPTEL. But the mostly the first half of the course is the mathematical background behind that group theory is there.
yes,
So and that is actually very interesting. And as well at the same time, it is a little, as it involves a lot of mathematics. Uh,
yes,
so it seems to be very hard, but that part actually is not taught in many of the institute. Even I have read from some institute of national importance, but that part was never covered. You
yes,
always get to who you always get to start from the symmetry point group, and then the application part, cells and other things. But one of the mathematical aspect behind the group theory,
yes.
that is discussed in that NPTEL course. So if you want to learn, then you can opt for that course also. I think that course is offered this semester or the next semester. I will have to check. Um,
Okay.
I think it is offered in this
And
semester only.
you are also associated with that course.
No, no, no. Once, I mean, I was once. Means I used to take that course also. But
Okay.
in NPTEL, I don't think I have taken that course. Means I have taught that course as a TA. I have taught that course. During our times, what happened that I got admitted during the COVID times.
Oh,
So our time, the lecture series was all online.
yes.
So that time, Professor Datta, what he has done was that we had to look at those lectures from the symmetry for the symmetry course from the internet, and then we used to discuss once a week in a class. That what we have learned. So by that way, we have in the COVID times that class was taught to us. It was interesting. Actually, the first half of the course was mainly the first 6 to 7 weeks or first 5 weeks was completely mathematical.
Yes.
So it's a little bit on the tougher side, but you can understand at the end of the day. Okay, so now let us go to the next part. Next part is easy. That we know that what is the outcome, right, of this centrifugal distortion constant. That when it is, how is the rotational spectrum is going to affect it. So see, oh, I do not have an extra page. I will need one. Wait. Uh, we know when there is no, so when it is a rigid rotor, then the energy gap is uh,
Less best. Very less best.
no, not the energy gap, sorry.
Okay.
The
J into
the
J plus one.
yes, this is in centimeter inverse. And
Yes.
when it is a non-rigidity comes, then we already, the expression is given, right? Ej becomes, this part is there, along with that the
Minus
distortion coefficient, right? And I think the
J.
j is there,
J. J.
j square is there.
J will come. Yes. J square will come.
So if one has to think what is the energy of j plus 1, then it is b j plus 1 into j plus 2. Simply in this case also, and it is b j plus 1 square and j plus 2 square. So the energy difference in this case is, we know it is come to be 2b into j plus 1. I am not doing much. And in this case,
That is 2b into J plus one
2b into j plus 1 is there, and effective
minus
1
4d minus 4d into J plus one whole cube.
whole cube, right? This term
Yes.
will come. So if you compare now these two, now if I use two different colors, maybe first I will draw the axis. Suppose this is my new bar, and now if this is for the rigid rotor, suppose I am trying to take all the concept inside that, which intensity there should be low or high. Okay, so maybe something like this. So this is for, if this is for the rigid rotor,
Yes.
then the line spectrum for the non-rigid rotor, suppose I am doing it in dots. So the first one would be here. The second one, sorry, I have done a mistake. This this would be decreasing. So the line should be in this side, right?
Left side.
Left side. And in this case, the line is shifted more.
Yes.
In this case, it will shift more. And it is what I'm trying to draw is the, for very small value of J, the concept we discussed earlier also, right? That the
Yes.
for vibrational levels also, that the anharmonicity effect only at very high value of, maybe we can show up to these only. I can, it is this. I think this is up to this part it will be clear, right? This, by this, how it is going to affect our spectrum. Now let us go to the next question. Next question is interesting. That what is the order of the acha? Yeah, I just remember this part. Yesterday we were discussing one question regarding the pitch of the
Yes.
thing, no? Pitch of the delay. So
Mhm.
see, there the question was that I actually took it for 1 femtosecond resolution, but it was written femtosecond resolution. See, nanometer resolution for a nanometer pitch, nanometer scaling for a pitch would be very difficult to prepare for a mechanical pitch, right?
Yes.
So, means by I will move it nanometer distance is actually difficult for a mechanical pitch. Means even if it is controlled by a computer and all. So the femtosecond resolution means it could have been 10 femtoseconds also, not really 1 femtosecond, right? So what I discussed with sir is that it it is in mic it will be in micron. So you may not get 1 femtosecond resolution out of the delay, but minimum what you are going to get at least 5 femtosecond or 6 femtosecond some resolution minimum. So
Yes.
if you are going to have a 1 micron pitch, so the answer would be micron. So if you are getting that question again, then please select micron only.
Yes. Yes. I don't have the idea. I took the minimum value. That's
Yeah,
why.
yeah,
And
1 femtosecond. Yeah, we also expect that if we are talking about femtosecond resolution, then we should get it at one
yes.
femtosecond also. But one
Yes. Yes.
femtosecond resolution would have been also difficult. What I have seen that I have shown you one setup for palm probe also, and we also
Yes.
have another setup of femtosecond optical gating. So that is another instrument for collecting fluorescence lifetime. But fluorescence lifetime, uh, the generally people use TCSPC, time correlated single photon counting, but that is for nanosecond, picosecond to nanosecond resolution. But the instrument we also have TCSPC as a central facility, but in our lab we have the femtosecond half conversion also. So that is, let me write it one. Maybe you can find it in femtosecond.
And sir, I have one question that
Yes,
your that total distance the mirror has to move for this femtosecond is like it was coming like 1.15 micron for
yes,
1 femtosecond.
one
Let's say.
femtosecond. Yes,
For 1 femtosecond, the total distance traversed by the mirror will be like zero point 0.1 zero point 0.1 micron. Okay.
yes,
Yes. And what is the meaning of a pitch? Means let's say you have a screw gauge. Okay.
yes.
Means once you rotate, how much distance it will travel, that is your pitch.
Hmm.
Let's say you have a screw gauge and you rotate 360 degree and
Yes.
the distance it will traverse, that
Move
is your
in the
pitch.
yes, move in the yeah, longitudinal scale is pitch.
Yes, 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 yes.
Yes.
And let's say you need multiple rotations,
Hmm.
full circle rotation to cover all this distance. I mean,
Hmm.
let's say I don't know. I am yeah, just arguing with you. Now,
Hmm.
let's say you have to rotate 10 times to
Yes.
achieve this zero point 0.1 micron here.
1.5. Yes. 1.5
Yes,
micron.
0.15. Yes, then you have to again divide. If anyone asks you what is the pitch distance, then you have to divide by again 10 times. Means 0.15 divided by 10. From
Uh,
that perspective, I did this year. It will be nanometer, and
uh,
it is completely fine that you have this knowledge. This you are currently working with this instrument, and
yes. Yes.
you know better than it
No.
is.
I
It
mean,
will be
if you move it by suppose if you do a 360-degree rotation, then what is pitch? Pitch is the how much it is moving on the longitudinal distance, right?
No, no, no.
So,
Pitch is after one full rotation, how much
hmm,
distance it will traverse.
huh,
That is called one pitch.
so that is so practically that we are thinking like that it is moving one time, and that is the minimum uh, distance
Yes,
it can go.
yes, yes,
So that for a 1 femtosecond, ideally we would have required the pitch of 0.15 micron then, right?
yes, 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 yes,
It
yes.
should have moved. Uh, if it would have moved 0.15 micron, then the light would have had to travel zero point 0.3
Micron.
0.3 micron, and then you have to do the rest of the mathematics. You will see that it will be 1 femtosecond.
I was thinking in that way. That's why I selected
Okay,
the nanometer.
okay. But it's good to know that thing also. But yeah, at the end of the day, you are now clear what you
Yes,
have to
yes,
do.
yes.
Yeah.
Right.
So in this instrument, what I was talking, you can later, if you are interested, I will show this instrument also. So this is known as femtosecond optical gating. In this instrument, what you can get is you can record fluorescence lifetime.
Yes.
But fluorescence lifetime, so this is a very specialized instrument. So
You know,
not
in our lab also some kind of in lab where I am currently
yes,
now
yes, yes.
working.
I think
This
Professor Sukhendu Nath's lab, I think you will find it. We are from BIRC, right?
yes, yes. I am working right now in actinide chemistry section in RCD,
Okay,
radiochem
okay,
division.
okay,
So I am now working with this Arunasis Bhattacharya. You
okay,
may know
okay,
or may not know.
okay.
So in that lab I am currently working.
So yeah, there you may find this. So it is better to if you can learn this instrument for your research purpose, then it would have been great if you can use it.
Yes.
So yeah. So so in this instrument also that we had, as we have to go to the femtosecond resolution, so you need to use that speed of the light as a tool in this kind of instrument. You cannot actually rely upon the electronics, only electronics, like what we do for TCSPC and other instrument. So there what happen is that even if you are using a ultra fast laser, what happens, suppose your pulse width in time scale, it is 100 of femtosecond, even less than that, but the the minimum the instrument response function, that means that that is the minimum the instrument can record, so that would become in picoseconds, 60 picoseconds, 70 picoseconds, even if you are using a very high end instrument.
Yes.
In that case, like, if you use a capacitor, other electronics, so there it becomes in picosecond. Even if you are using a 100 femtosecond ultra fast laser also.
Okay.
So that time, if your compound is very weakly emissive, or even if it is very highly emissive, but there is a very fast component in femtosecond scale, that can be missed in that instrument because of the resolution. So there you require this fog kind of instrument, or maybe the palm probe spectroscopy, where you can use this uh, femtosecond time scale. And for these you require that delay stage. So we had to rely upon the speed of light that is there for our savior. That acts as a savior. Yes. Now let us go back to the question that what is the order of magnitude of spacing between two successive lines in a grating? So we know we can use the this n lambda is equal to
2D time.
2d 2d sine theta, not actually 2d sine theta. For this grating or monochromator, so we will arrive at 2d sine theta. I will show you how, for not for this. So I think I have started talking about this part, and then I guess I did not had the writing pad that time, and I could not discuss that part on the first day itself. Maybe I will discuss that thing on the next day. Maybe first I will finish with the symmetry part, and if I am taking an extra class, then I will discuss that. So we'll mostly go with n equals to 1, the first order diffraction. So here lambda is your wavelength. So and we can take the maximum value of sine I and sine I can be equal to r, incident angle and reflective angle. So you will see the here it is 2d, and d is lambda by 2. So d is your spacing between two successive line, or you can say this is the groove distance, the spacing between the grooves. So it is said for a electronic spectroscopy UV visible region. So what is the UV visible region in terms of
Nanometer
nanometer
or
scale?
the in
Uh,
that
to
100 nanometer.
200 to 800 nanometer, maybe
Yes.
even 100 you can take. So the you can see your D will be something like 100 to 400 nanometer you will require in some range. So hundreds of nanosecond would be so you need to show this if this kind of question come hundreds of nanosecond, and
Nanometer
the
will be
yes, not hundred of nanosecond, hundred of nanometers.
nanometer.
So this kind of spacing is required, and this kind of spacing is actually there. And this actually mostly done by laser lithography kind of experiments. It cannot be possible by human or by us that we cut it or we create a spacing between that. Generally, I think it laser has been used to do that. Okay. Now, this is one of the very interesting question. That the question is that why is the fundamental transition for an anharmonic oscillator much stronger than the fast overtone? Firstly, that for an harmonic oscillator, uh, it was only delta V was only plus minus 1. But when the enharmonicity is introduced, then the selection rule become plus minus 1, plus minus 2, plus minus 3, like that, right? Fundamental overtone is 0 to 1, V equals to 0 to V equals to 1. What is the fast overtone? 0 to
0 to
2,
2.
right? And
Yes.
what is the second one?
0 to 3.
0 to 3. Now, what is the expected intensity scale, which would be higher?
The 0 to 1 transition will be
The
higher.
fundamental transition one.
Fundamental will be
Now,
higher.
what we are going to do is that we are going to mathematically come at the expression why we are going to get highest intensity for fundamental transition, and why low for the first overtone or the second overtone. And if we are going to discuss the transition probability, then what is the factor we should discuss?
The PV plus 1 by PV is equal to e to the power minus E by KT.
No, no. So that is the population, but that is one of the part. But first, when you are so if the transition is possible or not, if you have to talk about that, then which of the intrinsic property of a molecule will be required? Intensity is based on transition moment integral. If the transition moment integral is zero, then so your transition, even if your there is highly populated, your transition won't take place, right?
But we are talking about anharmonic oscillator, then all these transitions are possible.
All the transitions are possible, but that is what we are going to come. But
Yes.
for that, the important parameter to judge would be the transition moment integral. Is it uh, obviously your population is, you already know your population of the is zeroth state is highest. Okay,
Yes.
that is one of the point. Now, if you have to discuss in transition, we are going to discuss this problem in terms of transition moment integral. I think one of the assumption that has not been, it should have been mentioned that all the states are equally populated. If that was the case, then we only have to rely on the transition moment integral, or else what you are saying that is true. that v equals to 0 is highly populated, then it is much more stronger.
Yes.
Maybe that should also have been written here, that uh, all the states are equally populated. But for now, let us think about that. For the each of the states are uh, uh, each of the states are equally populated. Let us go by that assumption, and then we need to write down the uh, states or the wave function. Now, see, enharmonic oscillator is there. Harmonic oscillator is what we can start off with, right? Okay, because we can solve that simple harmonic oscillator. Now, for enharmonic oscillator, what we are going to assume is that the wave function will be that unperturbed harmonic oscillator wave function plus some perturbation in the wave function. And that
Yes.
perturbation we can actually write that we can write the perturbed wave function as a linear combination. So that is the usual thing what we do in perturbation theory also.
Yes.
Unperturbed function and closely did unperturbed. Because these unperturbed wave function, why we can do this? We can write it in a terms of linear combination, because this unperturbed wave function actually forms the total basis set of this Hamiltonian energy. So we can write the V equal to 0 state as the unperturbed one plus some coefficient, and your I cannot be 0 because we already have taken this into account. When I is 0, then this is psi v equals to 0 at 0. We are talking about the other close related states. And what is prominent here, that AI is very, very small quantity. This is some constant. So now if we can do that, we can write our fast excited vibration state also. We can write it in terms of the unperturbed wave function, and maybe we can take another bj as the small coefficient. So j 0 and j cannot be 1, right? Because we already took 1 here. Again, we can say bj is small. Then psi v equals to 2. We will only discuss these three because this is when we are going to discuss the transition moment between these two, then it is my fundamental, and these two would have been my first word. Ck psi equals to k. Now, how does my for a transition moment integral TMI, maybe for maybe I can write it in the next page. First of all, transition moment integral, let me write. It would have been psi final, your dipole moment operator, right?
Yes. Psi A.
then psi your I initial, which is
Also,
obviously in this case it is v equals to 0 in all the case.
mod square of this.
Uh, right. So we can only discuss about the mod square will be your intensity. So this
Okay.
is what your transition moment integral is. So your intensity is mod square of the transition moment integral. So we are only discussing about the transition moment integral here. So for your fundamental, your TMI is psi v equals to 1 mu psi v equals to 0. Now then it is actually please watch it what I am writing. If I am making any mistake, please let me know.
Yes. Yes.
So you need to do, we need to break it down into, as you can see, there are going to be four integrals are going to appear from this. But that is going to be very, very easy. We will write it in different colors maybe. See, first, let us do the easier one. You can see from here, so this is one of the integral, right?
Yes.
Then what is next? Maybe we can name it 1. Then what is the next one? Let us see. We will take v equals to 1. Then mu is there. We are going to deal with I equals to, I cannot be equals to 0. AI, II 0. Maybe we can write it in terms of, we can take, maybe I can take the summation outside. AI, and this is I, sorry, should be v equals to I. We'll discuss the fate of the each of the integral at the end. Let us
Yes.
first write down all the integrals. Next will be similar. Summation j cannot be equals to 1 bj, then iv equals to j first order, sorry, zeroth order, then your dipole moment operator, then you have this, and at the end, this is your third term, and your fourth term is I cannot be equals to 0, j cannot be equals to 1, ai BA, and it is I equals to J zeroth of this, and IV equals to I. This is the fourth one. Now let us discuss what do you think about the fast integral. What do you think of the fast integral? Means
First
I'm
integral, yes. First integral, we can think about that this integral will survive because one v equal to one is asymmetric part, and mu is your maybe asymmetric part is there. Then v is
means
zero.
clearly from our basic knowledge that the selection rule is just we need to see about the selection rule. Selection rule tell us that v equals to delta v should be plus minus one, right?
Yes, yes, yes.
For a I would say for a
Harmonic
when we
oscillator.
discover a harmonic oscillator thing. Now
Yes.
for that it will give me one will give me large finite value.
Mhm.
We are not going about the exact value, large finite value. What about the Acha? Another thing for this question, you do not have to think about the population first of all, because means that you're starting. So that assumption is not required because you think your starting point is v equals to zero. That is maximum anyway, right? For your fundamental and first overtone, there you do not have to think about the population. Population is same for v equals to zero, right? So here, yeah, my initial vibrational level is zero, v equals to zero. So I cannot compare it in terms of the population. I only have to compare in terms of transition moment integral. Okay, so that assumption is not required. Now, what about the second integral? Will it give me finite value? Means large finite value, small finite value, what? Let us see. I cannot be equals to zero. So if I cannot be equals to zero,
Mhm.
then you see it can be two, it can be one,
Yes.
it can be one, it can be um, so if it is one, then you see it is symmetric, and mu mostly
Positive.
anti-symmetric, so it is going to be zero, right?
Yes.
Then if it is two, then it may survive, right?
Yes. Yes. Yes.
Then it may survive. But you also have to see it is coming with one more thing that AI is there. AI is very small quantity, lesser than one in
Yes. Yes.
decimals. So it is going to give me a small finite
Yes.
value for all, only for I equals to 2. When I will become 3, 4, or even 1, then see it is going to be 0, right? In terms of if we think of delta v equals to plus minus 1, right? Now let us go to the third integral. What we are getting here, we are multiplying this integral obviously with a smaller quantity bj, but your j cannot be 1.
Yes.
Your j can be 0, then again the same problem, anti-symmetry. Your integral is anti-symmetric, then it is 0. What about j
Yes.
equals to 2? If your j is 2, then your delta v equals to plus minus 1 is not valid anymore, right?
Yes.
So it
Yes.
is going to be 0
Anyhow.
for all in this case, right?
Yes. Yes.
Now what about the last integral? Last integral is v equals to, so it is going to be a very finite, see, it cannot be 0. If I
Yes.
cannot be 0, then j cannot be 1. So that part is already being taken care of because your delta v can be plus minus 1 only. So
Mhm.
this will lead to to small finite value for j equals to I plus minus 1. And obviously your I cannot be 0 and cannot be 1. J cannot be 1. Okay. Means your I can be 1, J can be 2. Your I can be, uh, actually I should be very small, because here it is only one AI is there. Now it is becoming AI into BJ. So which is going to give me a very, very small term, right?
Yes.
So the finite value would be small. But at the end, what we are getting for this enharmonic oscillator, we are seeing that our transition moment integral is a summation of a large finite value plus some small finite values are also coming. Now let us see for the overtone what we are going to get. I hope it is making sense what we are discussing.
Yes.
So now let us discuss about the fast overtone. Then the transition moment integral is your psi v equals to 2 mu psi v equals to 0, which is nothing but, if I have to write it here, equals to 2 zeroth plus summation of k is not equals to 2 ck psi v equals to k 0. Now your transition moment integral, sorry, your dipole moment operator, then your psi v equals to 0th plus summation of I is not equals to 0. Your AI and psi v can be equals to I of 0. This is my integral. Again, I am going to get 4 integral.
No,
Let
no,
us
just symmetry will take care of. You can do it, sir. No
okay.
need to just break it down.
Let us break it down for once.
Okay, okay.
Uh, as we are going to compare with the previous one, no? So let
Yes.
us break it down once. So the first will be like this, first integral. Then the second one will be summation k cannot, it's not equals to 2 ck psi v equals to k mu. Acha, I have, in this case I have the earlier one. Did I do the correct thing or go for? Yeah, I have actually taken the fourth integral here. That's the first. Here I should have written I not equals to 0 AI. Then it would have been v equals to 2 equals to I. I hope I am doing the correct thing. Yes. Now, so this is my first integral. This is my second integral. Now the third one consists of again the one I was writing earlier. Ck v equals to 2. Sorry, v equals to k 0th mu. This is my third integral. And my fourth integral is again product of this I k is not equals to 0, k is not equals to 2, ai ck iv equals to k 0, dipole moment operator equals to I 0. This is my fourth integral. Now what about fast integral? From our previous discussion, what is going to be this?
Yes, that is going to be 0.
This is going to be 0.
0.
What about the second integral?
Yes. For v equal to 1, only this thing can survive.
What about v equals to 3?
V equal to 3, it can also survive. Yes, it
So
may survive.
only, so I equals to 2 or 3, finite, small finite value.
Yes.
What about the third integral? When k is 0, obviously
It will
antisymmetric
0.
integral 0. When
It
it
will
is
be
k
0.
equals to 1,
Only that time it can survive.
yes, what only that time. So k equals to
Yes.
1, small finite value. What about the fourth one?
It's only very small values.
Very, it will come as very small finite value, right?
Yes.
And at which value of I and k? I so I can if I can be 1,
Yes.
k can be 2, but that is not possible because my k cannot be equals to 2.
Yes.
Then if my I is 0, that is also not possible. So my I 1 is also not possible, right?
Yes.
So means even if it is possible, then whatever value of k would have been, it would be a
Yes.
integral would be 0. So I have to
Yes.
start from maybe I equals to 2. So,
Yes.
so there we are going to get very small finite value for I equals to 2 onwards, right?
Yes. Yes. This is
So,
actually I can now understand my previous assumption was wrong. That I cannot take this population into consideration. This is
why?
the right
Tell
way.
me.
Yes.
Yeah, because you are
Yes.
starting from v equals to 0 anyway, right?
Zero anyway. Yes.
So your uh, so your population thing is taken care of already because your starting point is same.
Yes. Yes.
So that's why you have to discuss this in terms of transition moment integral. Which transition is possible? Which state? Which state? Now you can see when you compare the transition moment integral of the fundamental and the fast overtone, you see the main point of difference is there in this large finite value, right?
Yes.
Which was
Yes.
there in case of the fundamental transition, which is missing in the case of fast overtone. So obviously, when I compare, I'm going to compare. Then what I'm going to find out? I'm going to find out the TMI of fundamental is very bigger than the TMI of fast overtone, right?
Yes.
So if my TMI is higher, so my as you earlier we were discussing, right, that intensity is the square of the TMI. So obviously my intensity of fundamental is going to even bigger than the intensity of fast overtone, right?
Yes.
That is actually the basic funda behind the thing what we are discussing, that delta V can be plus minus 1 plus minus 2 plus minus 3.
Question, sir.
Yes.
This mu is ultimately related to the energy that you are supplying. Na? This light, the light beam you are
No, this mu is the property of your uh, molecule, dipole moment.
dipole moment, and
Yes.
this dipole moment also interact with your
Uh,
oscillating electric field also.
right. And that oscillating field needs to create a change in the dipole moment for
Yes,
IR spectroscopy, right? Because this mu
yes,
is going to be a mu zero, a permanent dipole moment, plus d mu zero by I think d mu zero by dv or something like d uh, e, something like that term is there. That
it has nothing to do with,
dx.
yes,
The change in
whe-
the, yes.
yes, whether it has anything with the energy of the instant light, anything to do with this instant light. Let's say I have given a light, means I am
Hmm.
probing with a light which
Hmm.
has energy that is equivalent to the first order energy gap.
Hmm.
Let's say I am giving a light source which energy is comparable with the first order energy.
Hmm.
Then only this thing will resonate and the transition probability may be high. I don't know. I'm just asking.
Hmm. 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 See,
Then it will be higher than their fundamental, the transition. Whether it is
um,
possible.
I don't think so, because then only this. That energy part is dependent with the selection. So when we come to the selection rule, see, here we have also have done the derivation of the selection rule, right? During the selection rule, what we have done, uh, we have seen that the um, how delta v equals to plus minus 1 has come. That Hermite polynomial, that recursion relationship was there.
Yeah.
And I am just trying to remember that in the derivation process, if there was any energy term was there or not. I don't think so. There was any energy term, but here we learned what at the end of the course. What end of the day we learned that your gap, the your
Yes.
H nu, whatever energy you are providing,
Yes.
that is going to be equals to the, the so you are giving it H nu,
Yes. Yes.
and the gap between it was so H nu L, and
Yes.
the gap was something H nu. So your the photon you are providing will be the equal to the gap. Now if you are providing it double of that, and
Yes.
suppose I'm thinking that even my this is b equals to 2, v equals to 1, v equals to 0, it won't be possible, because first of all the transition moment integral is not dependent on the energy. So
Okay.
there itself, uh, the it is not going to be possible.
Okay. Means if I am going to provide, let's say, energy this H nu 2 to 0 means
0
the
to 2.
energy gap 0 to 2. Okay,
Hmm.
I'm just providing that much energy.
Hmm.
In that case, the transition will be maximum. In the case of 0 to 2 transition will be the maximum.
Yes, yes. See,
Uh,
for a fast overturn and all, I think you are already giving that energy, and that is why you are seeing that. Means this energy has been absorbed. So,
yes.
suppose what do you mean by you can see a transition line in the spectrum, or you can see a spectrum. So so these are absorption spectroscopy, right? IR, these are absorption spectroscopy. You are providing an energy, and it is uh,
Yeah.
uh, getting absorbed and showing that absorption line, right? So what I'm trying to say that you are providing all the energies. Now, suppose when you are giving V0 to 2 energy, it will absorb, but the absorption will be very, very less, because the transition moment integral is less.
Okay. It may
Mm,
be we are providing the white light, that's why
yes,
TMI
yes,
will
yes,
be high.
yes. Because anyway, so when you do a absorption spectroscopy or IR spectroscopy, what you do that you are providing it all the energies,
Yes, yes.
right?
No, first of all, we provide all the energy, then take a scan, and ultimately we excite at the particular wavelength.
No, we excite at all the wavelengths, not at a
For
particular
the
wavelength.
wavelength, yes, for the emission part, we excite at
For
particular
for
excitation.
emission, we excite at a particular.
Yes, yes, yes. Yes, that is the thing.
Okay.
Okay.
Okay. Now let us go to the using Taylor series expansion of the potential energy of an enharmonic oscillator. Knowing the expression of the coefficient, what it is actually trying to say is that see potential energy of a enharmonic oscillator. So what do we know about the potential energy? So your
It will be more
potential energy,
potential.
Morse, obviously it is going to Morse potential for an harmonic oscillator, but for a
Yes,
harmonic oscillator, what is the potential? Half kx square.
yes,
So now if anyone tell me to write it in terms of Taylor series, so I can write it like C0 plus C1x plus C2 x square like this,
yes,
C3
yes,
x cube, C4 x to the power 4, and that's all. But now what we know for a SHO, this is the case, right?
yes,
Simple harmonic oscillator. So that means my C2 is k by 2. Now for enharmonic oscillator, so we are treating it as a perturbation problem.
yes,
So my perturbation can come only after C2 then, because my C0 and C1 is already 0, right?
yes,
For in the terms of simple harmonic oscillator, right? My
yes,
C0
yes,
and C1 are 0. So now only these C3, C4, these terms are uh, going to take part. But we
yes,
also have to understand that this C3 is going to greater than C4, but obviously my C2 is very, very greater than C3, right? Because in the denominator, your that part is going to increase. So your perturbed energy. So how do we do energy? How do we look at the energy? Energy is so perturbed energy. Sorry, today my handwriting. I'm trying to do it fast. Handwriting. So it is if my wave functions are normalized, so I can write it in like this. My perturbed Hamiltonian, right?
yes,
So this is your C3x cube plus C4 x to the power 4. These terms are my can come as a my perturbation. Now,
yes,
when that comes as a perturbation, now see the problem becomes very easy because the wave function doesn't matter if it is symmetric or anti-symmetric, whatever my value of v is.
yes.
It is going to depend on the symmetry of my uh,
Only one still survive. You want to
yes,
say, na?
yes. So see only the even CNs are going to survive, are going to or I should write affect the ion. If it is the C3, C5, C7, those are going to be
Yes, yes,
become zero. So
yes,
what is this is a going we can break it in terms of C3 x cube psi v 0. We can break it in terms of then C4 x to the power 4 psi v 0 like this and
Yes.
all. So only the even CNs are going to survive, and that is going to add up to
Contribute.
my energy expression. Only this part is necessary for the discussion. You don't have to write the exact values.
Oh,
Okay.
yes.
And okay, now let us go to the next question. I think next question was this, and I'm not going to discuss this because this has been done in the class. This is that the Fermi's golden rule, the
Yes.
derivation. So let us not discuss it here. So this part I will try to discuss this maybe after the that discussion that groups and all. That part I have not touched it yet. So if I just give you the formula and just do the math, then it is not justifiable. So I will first try to discuss that relationship between the effective bandwidth, slit width, and all, and then I will discuss that. We can start from the second question. So the second question says the spectrum is recorded from 500 centimeter inverse to 400 centimeter inverse in a dispersive mode with a resolution of 1 centimeter inverse and the integration time of zero point 0.1 second. So what will be the acquisition time? Can you tell me what will be the acquisition time? The resolution is 1 centimeter inverse and
Yes. Yes.
integration time is zero point 0.1. That
Yes.
means
Yes. That will
per
be
1
3,000.
centimeter,
Yes. 3,500 divided by point 0.1.
not
This
divided
will
by, multiply by.
multiplied. Yes. It's multiplied. Yes. Yes.
So
Yes.
it would be something
Multiplied.
like 350 seconds, something like that, right?
Yes. 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 Yes.
Okay, so I'm not writing it here. So how much time will be required to record the spectra with the same resolution and signal to noise ratio using the Fourier transform spectroscopy? Means you can give me a approximate value.
The required to record using Fourier transform spectroscopy.
That means in time domain. So in dispersive mode means we are doing it in energy domain or frequency domain. Now
Yes.
suppose if you have to do it in time domain, then how much time would it been required?
But it's a relation I forgot.
It is actually going to require only that first scan only, one scan. In one
Yes.
scan,
Yes.
all
Only
the
one single one snapshot you can record all these things. Yes. Yes. Yes.
so as the integration time, as you can see, it's zero point 0.1 second.
Yes.
So it will take only zero point 0.1 second to record all this. Even if you try to do it once or twice or thrice, depends on how much average you want to do for the signal to noise ratio. Improve
Yes.
it.
Yes.
So that's all for this question. Now let us go to the second question that derive the expression for the maximum population for a rotational level at a particular temperature T. That was what we were discussing earlier, right?
Yes. 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 Yes.
Your this is 2j plus 1, your degeneracy exponential
Minus EJ
minus
by KT. EJ
ej
by
by kt. kbt.
KT.
I can also write it in. Right?
Yes.
Yes, in joules, and now I have to, if max for maxima, my this should give me an inflection point. So if I have to do a derivation against this, so this is a UV kind of a means I have to do a product. So I have to do for a derivation for once, and then I have to take that other thing as a constant, and then so the first thing would be two. If I have to do a derivative of 2j plus 1, then 2, and I have to keep my exponential term as constant. Now I have to do this. So plus 2j plus 1 as constant. Then exponential of this term. So this will first same be with a minus sign obviously because the minus is there, right? And I also have to take care of the j into j plus 1. That is j square plus j. That means 2j plus 1.
Plus
So it is effectively 2j plus 1 square. That would be equals to 0. Now so my exponential term cannot be 0, right? So I can take it as a constant and I will write it as 2 minus 2j plus 1 square. Am I making any mistake? I think so. So when I am going to do this,
yes,
I
this
forgot the constants. So
yes,
that would be uh,
BHC by cavity.
BHC by QT. C by QT. So what I want to get, so this is going to my J max.
Yes.
Then it will happen. Then it is 2J plus 1 square is going to be
270.
if I
Yes.
to
Yes. Remove the minus sign.
hmm,
Not equal.
I just not do this deep jump and just write it and then 2J
Mm,
plus 1 square would have been 2 kBT
by BHC
by base
and Jmax
and
equal. Or you can directly write this.
so I will directly write JMX is going to be I have to divide it by so it is going to be minus 1 and
Mm.
2 kBT 2 I have to divide it by 2 so kBT
By 2
2
BHC
BHC
minus
by
half.
so this is the equation I'm going to arrive at for JMX. So I thought that it is better to do once at least in the class. So okay. Now this is another question. Prove the maximum value of magnetic quantum number M is going to be J for a rigid rotor. So how do you want to approach this plot? The maximum value of magnetic quantum number. You already know you if your J is suppose your J is 1, then what are the possible value of M are?
0 plus minus 1.
0 plus minus 1. So the maximum value is 1 or the magnetic
Yes.
maximum possible amplitude is 1, right?
Yes.
Okay. Now how can you do that in mathematics? So that is so we are doing it what that thing is called we are putting the values and we are telling them.
Yes.
But how can we do it? So suppose uh, how
That
m
was
how m and j are related.
yes.
If you remember this. So if this is my angular momentum vector and this is going to be my j into j plus 1 root of that h cut. This is my magnitude, right, of
Yes.
this vector. And it is making an angle theta. Suppose this is z axis and this is going to be my image cross, right? So what is this? So my cos theta is base by hypotenuse
Mm-hmm.
image cross divided by j into j plus 1 h cross, which is m by root over j into j plus 1.
Yes.
Now, what is the maximum value of cos theta? That is 1
Plus minus one. Yes.
plus minus 1. Means maximum value if we in terms of here is 1. So let
Yes.
us take that value. If we take that value, then you will see that your wait your if the theta is 0, then only this is going to be equal, right?
Yes.
And when the theta have some value,
Mm-hmm.
then the value of theta is going to be less than 1.
Yes.
So your aim is always going to be equal to and less than this, right?
Yes.
Do you get my point? What I'm trying to say?
Yes. Yes. Yes, sir.
Only for theta equal to 0, it is going to be equal.
Yes.
Other value, it is going to be less. So if I can write it in terms of like j square plus j. Now you see that for j equals to 0, j equals to 0, this is possible. M can be equal to
Mm.
like that. Now for j equals to 1, it is M is always going to be less than equals to 1 square plus 1, that is 2, root 2.
Yes.
That eventually means that it is going to be less than 1, right? Less than equals to 1. If it is 2, then M is always going to be less than equals to 6, root over 6. So
Mm.
by analogy, you can say that this is actually less than equals to G, a modulus. This is a mathematical way to say that how your magnetic quantum number m is always going to be. So it has a limiting value. It's not like it is always going to be less than, right? There is one option when it is going to be equal to your
G.
j. So, and that is the part. Now, if you remember that it is actually never going to be equals to j square plus j, root over j square plus j, because this situation is going to arise at theta when theta will be very very small. And if you remember that, what does this mean? When j equals to 1, that means your angular momentum have three orientation in space, three kind of. So suppose when j equals to 2, so then if it is z axis, so it is something like plus 2. So plus 2 in, so this is plus 2. This is this side is plus 2, plus 1, 0, -1, -2. Right? So there could be 5 orientation in space for your angular momentum operator. So that is what. So now you can see only at j equals to infinity you expect your theta to be close to zero, right? Theta is what? The angle between your z axis and the orbital angular momentum vector. So so that's why the limiting value is j, not j square plus j. Are you getting my point? What I'm trying to say? Actually, your m could have been root over 6, which is greater than 2, right? For j equals to 2, what is the notions we are getting? That notion is that if j equals to 2, then m can be less than equals to root 6. But what is the maximum value of m we get for j equals to 2? That is 2. So m is actually not equals to root j into j plus 1. So what I was discussing is that see, for j equals to 2, what you expect is m, the maximum value of m can be root over 6. But that is
Yes.
not the case. The reality we get for j equals to 2, m is 2 2 1 0 minus 2 minus 1. There are 5 orientations in space for orbital angular momentum vector.
Sir,
But
you can support this by saying that these all these things are quantized, so it cannot take this integer. I means it can only take the integer values. It cannot take this kind of 1.5 or
no,
this two.
right. That is another part.
Yeah,
That is another way of saying it, maybe.
yeah.
But what I'm trying to say that at j equals to infinity, you expect that m is close to the root over j plus j, root over j into j plus 1. Still, it
Yes,
is not, right?
yes,
So that is
yes,
what the question is, that the maximum value of magnetic quantum number m is j, not root over j square plus j. Okay.
yes.
Okay. Now, what is the next question? Next question is the last question, I guess. Yes. So let us discuss that. Uh, that it is saying that consider transition between j equals to 0 to j equals to 1 for a rigid rotor. So what do we expect? How many transition do we expect? J equals to
Pardon,
0
sir.
to
0 to j equal to 1 for a rigid rotor. What is the change expected for applying
no.
an electric field?
I don't think about the second part. First, tell me that if you are thinking about transition from j equals to 0 to 1, so how many transition you are
Yes.
expect? One, and that too
One,
at
only one
2b,
condition.
and that too at
Yes, yes, to be,
2b.
to be, yes.
Now now comes the second part. That what is the change expected when when the spectral line corresponding to that is uh, means you are applying a electric field upon that. Now,
Yes.
what do we expect to the transitions?
Okay. Upon changing the electric field. Okay.
So when there is no external electric field, okay, no
Yes.
along z axis or
Mm,
this axis, depending on your dipole moment also. So
mm,
fast j equals to 0 to j equals to, so if you think about the degeneracies, so for
mm.
the j equals to 0, it is only one state is there, singly
Yes.
degeneracy. Now it is j equals to 1. There are actually three states which are j equals to plus 1, 0, j equals to minus 1. They are degenerate. Yeah. Now when you apply an electric field, external electric field, that time you
Okay, this degeneracy will be lifted. Okay, you want to say
lifted.
that thing.
Yes, yes.
Okay.
Now you see your j equals to 0 will be at j equals to 0, but j equals to 1, there comes three states. J equals to plus 1, j equals to
Yes, yes,
0, j equals to minus 1.
yes,
Right?
yes, yes, yes,
Uh,
yes,
Actually, not j equals to plus 1, m equals to plus 1, m equals to 0, m equals to minus 1.
yes, yes, yes.
And then the selection rule actually becomes mj is 0 plus minus 1. So you are going to see three lines.
Yes.
Earlier, when there was no external field, there we expect one line, but now you are going to expect three lines. And this is
But I
known
want to
as
say
Stark
one
effect.
thing that
Yes.
okay, this is gonna start.
Yes.
But this B only depends on J. It will not depend on your M.
Now,
This 2B
which
you are talking about.
no,
This
I'm not talking about 2B anymore. I am talking about
okay.
how many transitions now you will see.
But if they are same, there is no spacing in between them. Means all are at same energy. All are having this same
No,
energy.
oh
Then
sorry.
how can you discriminate all these things?
No, no, I think there is going to be some change. Let me think of it in that sense. Suppose earlier the case was j equals to 0 to j equals to 1. So this is my energy
Equal to
scale.
one.
Huh?
Yes. Yes.
Now when I have added an external electric field, what I am
Hmm.
expecting my energy levels to be split like this. It's not degenerate anymore. So they have different energies right now. Okay.
Okay.
So it's still here my mj equals to 0. Here my mj equals to minus 1, mj equals to 0, mj equals to plus 1. So this is one possible transition. This is another possible transition. This is
Yes.
another possible transition.
Okay.
You're getting my point, what I'm trying to say here.
Yes. 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 Yes.
So earlier you had only one line. Now you are going to have three lines. But I'm not sure what you are saying was that the what was the gap is going to be something like that. Maybe it is going to be
Yes. Yes.
2B.
Yes. My concern is like that.
So that I also have to check once. It maybe depends on the no. Let me think. Again, population doesn't really matter because we are studying from the same state. It is going to depend on the I think the transition moment integral. They are again similarly. It is going to be dependent on the transition moment integral, and that in
But
terms.
sir, we are consider here we are taking the simple only simple expression when these
Hmm,
things will when this degeneracy will be lifted. No, then there will
hmm.
be there must be a separation between two b. There will be like 2b1 or 2b3 will be there. There
Yes,
must be thing like that.
yes, yes.
It will
The
not. It will
transition
never be
lines are
like
yes. They are not going to
yes,
be like that. This line, it is never
yes,
going to be. This is never going to be 2B. This is never going to be
yes, yes,
2B.
yes, yes.
What I
Only
was
in the
saying
case
that
of 0 to 0, only in the case of 0 to 0, there will be 2b.
yes,
But
this
I
might
think
be
other
2B, and
yes, yes,
this
yes,
one have to see.
yes, yes.
Okay. Okay, then I think I had these many questions, and actually these questions I have typed myself by looking at the this year's question. I did not have a
Okay.
good image of that. So the rest of the questions are similar to the previous year's question. These questions, this fundamental transition, fundamental fast overtone, why it is different, and then
Yes.
think of the Taylor series in terms of that, and these kind of questions are only there. So maybe the next week we'll discuss the symmetry related problems
Yes.
and
Yes.
how to get the point groups corrected. I can give you one website, name of a website
Okay.
where you can get very good idea of the character table spectra. Let me see if I have it in my Chrome. Symmetry Jacobs something. Jacobs University. But so here means you can, I think you can also see a individual molecule what is going to be the point group. Or I think that was another website. Let me check. You think you are going to get examples also.
Yes.
You can see the individual, I think, not this one. Maybe on the next day I will show you on online. You can see this symmetry at Otterbein. This one. This is a very nice website.
Okay. Okay. Actually, sir, I am from physics background. Now, that's why
Yes, I
never,
understand.
uh, I never went through this. This I went to this symmetry operation, all these things. But this detailed, yeah, I never read.
Okay. Actually, what I believe is that physics is harder than biochemistry. You are learning chemistry from a physics background. I don't know how it would have been turned out for me if I have to learn something. Means I will try my best, but I know it is going to be very difficult.
You know, your quantum mechanical knowledge is better
Quantum
than
chemical, no, no,
any else.
quantum chemical. In physics,
Means
the quantum mechanics is even.
yes,
I think it is even hard. I think the conventions are also a little different. Maybe on the next day,
somewhat, some.
maybe on the next day, I'll show you how you can see the individual. Uh, Means you can visualize the planes or the symmetry.
Yes, this all these things. Yes, yes.
Did you see here? You can see the
This
C2
H2O
axis.
molecule. Yes, H2. Yes, yes, yes.
Even for staggered ethane, methane, even I think they have it for higher molecules also. So this is one of the website you can look at. And now you can go to gallery. Now you can maybe think of ferrocene. So how does it? What is the point group B. First, you think by yourself and then
Yes.
try to associate where the symmetry elements are. When you
Yes.
play
Yes.
it, I
Yes.
think it will play. So this is a good website. I think you can see it. Maybe the next day we will discuss it further. So maybe with that we can stop today's session, and on
Yes.
the next day we will discuss the symmetry aspects next
Yes.
week.
Yes.
Okay. So thank
Yes.
you for
Yes.
joining,
Good night.
and
Good.
good night. Good night.
Good. Bye.